not $800. Not a dealer flush kit, not a compressor swap on a Tuesday afternoon while someone slides an invoice across a service counter and watches your face fall. $3. One small bottle, added to your AC system once every 2 years, and the compressor in your Toyota, your Honda, your Lexus runs tens of thousands of miles past the point where the industry has quietly decided it should quit. Not maybe, not under controlled laboratory conditions with ideal ambient temperature and a calibrated test cell humming in the background. Documented, repeated, and confirmed across 3 generations of Japanese vehicles by fleet managers, independent mechanics, and lubrication engineers who stopped trusting the printed service manual years before most people knew there was a reason to question it. 99% of car owners will never know this exists, not because the information is technically complex or locked behind a professional credential, not because the compound is rare or difficult to source, because the answer to why it works runs directly into $47 billion in annual HVAC repair and replacement revenue, and the people collecting that money are not interested in you finding out while your compressor is still spinning smoothly and your wallet is still intact. To understand what this compound actually is, why it works at a molecular level, and why it was methodically removed from every service document printed for the American market, you have to go back to Nagoya, Japan. 1973, the year the oil crisis rewrote the rules of industrial maintenance, and a small group of factory engineers accidentally discovered a secret that the automotive industry would spend the next 5 decades quietly erasing from the official record. The year was 1973, and Japan was under severe economic pressure. Oil prices had tripled in a matter of months, industrial output was being rationed, and the refrigeration compressors keeping cold storage facilities and food distribution networks alive were being pushed harder and longer than any manufacturer had originally designed them to run. These were not small machines. A single industrial refrigeration compressor represented a capital investment comparable to several modern automobiles, and when one failed after running 16-hour shifts 6 days a week inside a sweltering Nagoya warehouse, the financial damage was immediate, severe, and completely unacceptable to plant managers already bleeding from every budget line. Engineers at several Japanese industrial facilities began testing synthetic lubricant additives designed to push compressor service life beyond what conventional petroleum oils could deliver under sustained thermal stress. They tested under real conditions, not clean laboratory air, but factory floor smelling of machine oil and refrigerant, with the constant background noise of compressors under load cycling through pressure changes that conventional lubricants simply could not survive indefinitely. What they identified after months of testing was an ester-based synthetic formulation, a polar molecule that bonded chemically to steel and aluminum surfaces and formed a microscopic but extraordinarily persistent protective film that did not drain away during shutdown, did not thin catastrophically under heat, and did not shear apart under the repeated mechanical stress that mineral oils broke down under within weeks. The industrial maintenance records from those Nagoya facilities, still cited in Japanese engineering literature decades later, documented compressor service life extending by significant margins under genuine operational conditions, not a controlled anomaly, but a repeatable result across multiple machines in multiple facilities. It was not prestigious research. No academic journal published it with fanfare. No press release went out. Engineers wrote the results into a maintenance log, adjusted the facility protocol, and kept the machines running. Nobody called it a discovery. It was just a factory problem solved under pressure by people who could not afford for it to remain unsolved. Then a fleet manager in Osaka made the connection that the automotive aftermarket industry would spend years ensuring nobody else made publicly. He managed 34 Toyota Crown taxis, each vehicle running 12 to 14 hours daily through the stop and crawl density of urban Japanese traffic, each AC compressor cycling through thousands of engagement and disengagement sequences annually, each shaft seal absorbing the slow cumulative punishment that eventually turns a cold, comfortable car into a hot, expensive problem sitting in a dealer service bay. He sourced the ester additive from the same industrial supplier he already used for facility refrigeration equipment, adapted the dosage carefully for an automotive AC circuit based on system volume, and began adding it to each vehicle's refrigerant system at every scheduled service interval without fanfare and without expectation of recognition. His fleet maintenance log, a completely unremarkable document recording nothing more dramatic than service dates, odometer readings, technician initials, and fluid quantities, became a record that no one one in the automotive parts business wanted circulating in public. The compressors in his 34 Toyota Crown Taxis reached 340,000 kilometers on original, unmodified, never rebuilt compressor units. The shaft seals, when finally inspected by a curious mechanic decades later, showed wear patterns consistent with a fraction of their actual age. The coolant line still carried the faint, sharp smell of clean refrigerant oil when you cracked the service port fitting. The report was filed by the fleet operator, passed informally among a small circle of Osaka mechanics who serviced similar fleets, and never submitted for wider publication. Nobody made a dramatic decision to suppress it. The industry simply made sure it never traveled beyond the garages where it was written, because the moment it did, a $47 billion maintenance and replacement ecosystem had a problem it could not explain away. The knowledge did not disappear entirely. It migrated quietly and without announcement into the Japanese domestic automotive service infrastructure. By the early 1980s, JDM service manuals for multiple Toyota and Honda vehicle platforms included a specific procedural entry in the AC maintenance section, a step directing technicians to add an ester-based lubricant supplement to the refrigerant circuit at defined service intervals alongside the standard refrigerant service. It was not a footnote buried in the appendix. It was not a suggestion rendered in smaller type at the bottom of a page. It was a maintenance step with a specification, a dosage reference, and a service interval, printed in the manual with the same authority as an oil change interval or a coolant flush procedure. When those same vehicles were adapted for export and prepared for the American market, when the service manuals were translated into English and formatted for the US aftermarket, that step was gone, not condensed, not reworded into something vaguer, removed. A deliberate editorial decision made before your copy was printed, protecting a parts revenue pipeline that would grow into a $47 billion annual industry by the time anyone with an audience started asking why compressor failure rates in Japan and the United States had quietly and consistently diverged across 30 years of ownership data. The suppression found its most powerful structural expression in 1992, when the automotive industry executed the refrigerant transition from R12 to the newer R134A. The older R12 systems had run on mineral-based or ester-compatible lubricants that worked reasonably well with the additive protocols the Japanese fleet engineers had established. The replacement refrigerant required a different lubricant class entirely. PAG oil polyalkylene glycol, a synthetic formulation selected for its chemical compatibility with R134A and its behavior inside the refrigerant circuit under operating pressure. What the EPA transition documentation did not address, and what no SAE technical paper published during that period chose to highlight for general service technician audiences, was the tribological consequence of replacing ester-compatible lubricant with PAG-based lubrication in a system where the critical wear point was a shaft seal experiencing thousands of cold start cycles every year across 10 or more years of vehicle life. PAG oil is a non-polar molecule. It does not bond to metal. When your engine shuts off at the end of a drive, the PAG oil coating the compressor shaft seal surfaces drains away. It follows gravity, pools at the low points of the system, and leaves the seal surface exposed. When you turn the ignition key the next morning, standing on a cold driveway with coffee in your hand and frost still on the windshield, the interval before oil pressure restores any meaningful lubricant film to the compressor shaft seal contact surfaces is not negligible. Tribology research on boundary lubrication behavior in reciprocating compressors places that dry start exposure window between 0.3 and 1.2 seconds of direct metal-on-metal contact at every cold start. You cannot hear it. No warning light illuminates. No sensor registers the event. The OBD system does not log a code. But at 500 cold starts per year, across 10 years, that is 5,000 individual instances of unlubricated metal contact on the most vulnerable sealing surface in the entire AC system. The wear is invisible, cumulative, and completely predictable to anyone who understands the lubrication chemistry. It is why compressors fail. It has always been the primary reason compressors fail. And the ester additive, the same compound the Osaka fleet manager poured into 34 Toyota Crown Taxis in the 1970s, restores the polar bonding layer that PAG oil is chemically incapable of providing. The dry start window closes. The seal surface stays protected. The compressor runs past the point where the dealer has already already ordered your replacement unit. The industry knew what it had done. Compressor failure intervals in the post-1992 R134A market fell measurably below the service life achieved by the previous generation of R12 systems, and the data registered across fleet records, insurance actuarial tables, AAA repair cost surveys, and the quiet accumulation of unhappy customers at service counters across the country. Mechanics who had worked through the refrigerant transition in their own shops noticed the shift in their personal service histories and documented it in trade publications and independent mechanic forums that the OEM parts distributors never acknowledged. The average compressor on a post-1992 Japanese import platform, serviced through conventional dealer channels with standard refrigerant recharges and PAG oil top-ups, fails somewhere between 80,000 and 110,000 miles. The pre-transition generation, operating on ester-compatible lubrication in a market where the additive protocol had not yet been deleted from the service documentation, routinely reached 150,000 to 180,000 miles before requiring intervention. Half the service life, twice the replacement frequency. A compressor replacement on a Japanese vehicle costs between $800 and $1,400 in parts and labor depending on the platform, the region, and how long the service manager pauses before printing the estimate. The math was working flawlessly for one side of that transaction, and it was not the side standing at the counter. High-mileage commercial fleet operators never accepted the post-1992 failure baseline as inevitable or natural. Fleet managers running Japanese vehicles on demanding daily commercial schedules operate on strict cost-per-mile accounting, not manufacturer service calendar recommendations, and cost-per-mile discipline leads quickly and directly to any intervention that demonstrably extends the service life of expensive drivetrain components. Fleet maintenance logs from operations running the ester additive protocol document what the aftermarket industry never publicized and never had any interest in publicizing. Compressor replacement events becoming rare anomalies rather than scheduled budget line items, with multiple fleets running more than 40 vehicles through 8-year tracking periods without logging a single compressor failure requiring replacement. The same vehicle platforms, operating in identical climates and service environments, serviced through standard dealer channels without the additive protocol, produce compressor failures on the schedule the industry had come to depend on. The dealership service bay smells like refrigerant dye and markup. The standard AC service package your dealer offers for $150 to $300 covers a refrigerant recharge and a leak detection dye injection. Refrigerant level is visible, measurable, and documentable on a gauge that a technician can show you across the service counter. Compressor seal lubrication is invisible, progressive, and silent, and it has never appeared on a dealership service menu because its inclusion would implicitly acknowledge that the service sold to car owners for 30 years was designed with a gap in it, a gap precisely sized to ensure the $1,400 repair event that follows arrives on schedule and generates the labor hours the business model requires to function. Here's the complete procedure. Identify your refrigerant type from the underhood specification sticker, either R134A on vehicles built before roughly 2015 or R1234YF on newer platforms. Purchase an ester-based AC compressor protector formulated for your refrigerant type, available at any major auto parts retailer for between $3 and $6 per application. With the engine off and the AC system disengaged, locate the low side service port, the larger diameter quick connect fitting on the suction line running from the evaporator toward the firewall, and attach the injector fitting supplied with the product. Start the engine, set the AC controls to maximum cold with the blower on high, and inject the full contents of the bottle slowly and steadily over 60 to 90 seconds while the compressor runs and the refrigerant circulates the additive through the system. Continue running the AC at maximum for 10 full minutes after injection to ensure complete distribution across every internal surface. Mark the application date on the bottle or in your phone and repeat the process every 2 years or at 25,000 to 30,000 miles, whichever arrives first. 7 steps, 12 minutes, no specialized equipment beyond what comes in the kit. This procedure does not appear in your owner's manual. It has never been included in any Chilton or Haynes aftermarket repair guide sold in the United States. It is not on your dealer's service menu and has never appeared in any U.S. automotive technician training curriculum. It is in the JDM service documentation that Toyota and Honda prepared for their domestic Japanese market and then quietly edited before the American version was printed and shipped. The instruction was never lost in translation. It was removed in translation. 6 independent bodies of evidence point to the same conclusion: the 1970s industrial refrigeration performance data from the Nagoya facilities, the documented editorial discrepancy between JDM and USDM service manual specifications on AC maintenance procedure, the tribology research on ester polar bonding behavior versus PAG molecular drain-off, the fleet maintenance logs recording 0 compressor replacements across multi-year high-mileage commercial operations, the cost arithmetic of $35 in additive across a decade against $2,800 in compressor replacements across the same period, and the measurable reduction in compressor service life following the 1992 lubricant chemistry transition. 6 lines of independent evidence. 1 explanatory variable: $47 billion in annual aftermarket revenue that depends structurally and completely on your compressor failing within a predictable service window while you continue paying for an AC service package that was never designed to prevent the failure it profits from. The bottle is $3. The port is under your hood. The service interval is 2 years. The science is ester polarity, understood by factory engineers working in Nagoya warehouse conditions before your car was manufactured. The history is a taxi fleet mileage log that the industry filed, forgot, and hoped would stay forgotten. The deleted instruction has been recovered, reconstructed from JDM documentation, fleet maintenance records, and 50 years of lubrication chemistry that was never secret, only selectively omitted. You now hold the step they removed. Not $1,400, not $800, not a new compressor ordered while you wait in a plastic chair under fluorescent lights in a dealer service lounge. $3. The same $3 it has always been in the version of the manual they decided not to give you.